Good morning. Good morning. Welcome to the fourth day of the 2025 AIAA SciTech Forum. I'm Steve Frick. I'm a senior principal at Lockheed Martin Space and a member of the 2025 SciTech Guiding Coalition. We've talked a lot this week about how AIAA is a community, and in the spirit of compassion with our community, we want to acknowledge that many of our members and colleagues in California are suffering from the raging wildfires. We've seen that JPL is closed, and the staff there are dealing with this dangerous situation. We send our heartfelt support to them. We also want to join the nation today in remembering President Jimmy Carter on this National Day of Mourning. Our community especially remembers his contributions to space exploration and his greeting on behalf of humanity that was etched on the golden record and packed on board the Voyager spacecraft when it launched in 1977. In anticipation of possibly encountering other life in the universe, his words from 47 years ago continue their journey in interstellar space today, as we heard from Lori Leshin on Monday. They seem appropriate to hear again. The message says in part, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We're attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe." Thank you for pausing this morning to pay homage to President Carter through this solemn observance. Now let's continue our work on accelerating aerospace innovation for the future with today's program. As we all reach towards our industry's sustainability goals, we have the opportunity to celebrate members of the aerospace industry that are providing a vision of sustainable aviation technology and systems. During the Sustainable Aviation Workshop at 9:30 this morning, NASA Aeronautics leaders will share an overview of the agency's vision and strategy for sustainable aviation and host a panel discussion with the recent Advanced Aircraft Concepts for Environmental Sustainability 2050, or ACES, awardees. This initiative challenged industry and academia to come up with studies to push the boundaries of possibility for aircraft concepts, key technologies and designs that could offer the transformative solutions needed to secure commercial aviation's sustainable future. NASA issued 5 awards, and they went to Aurora Flight Sciences, Electra, Georgia Tech, Jet Zero, and Pratt & Whitney. And you'll be able to hear from these organizations at today's session. Today's schedule also offers 2 great ways to connect with your fellow attendees. 11:30 this morning, join us here for the networking lunch. Seating's available here in the Winterberry Ballroom. And at 6 p.m., join us for the Women at SciTech panel and social hour. Our distinguished panelists will discuss diverse voices, united impact, women driving the future of aerospace. This is a can't-miss opportunity to hear from women who are leaders in their fields. Now turning to the plenary panel, our high-level theme today is software and emerging AI. To kick us off with a panel with a discussion of AI and autonomy, we've assembled an impressive panel moderated by Dr. Julie Shah, professor of Aeronautics and Astronautics and leader Interactive Robotics Group, Computer Science and Artificial Intelligence Laboratory, MIT. Professor Shah's interests include autonomous systems, human-robot collaboration, AI planning and scheduling, and interactive robotics for aerospace, medical, and manufacturing. Before joining MIT, Dr. Shah worked at Boeing Research and Technology on robotics applications for aerospace manufacturing. She's developed innovative methods for enabling fluid human-robot teamwork in time-critical, safety-critical domains ranging from manufacturing to surgery to space exploration. She's received numerous awards and recognition, including an NSF Career Award for her work on human-aware autonomy for team-oriented environments. And her work on industrial robot collaboration was also recognized by the MIT Technology Review as one of the 10 breakthrough technologies of 2013. She's also received international recognition in the form of Best Paper Awards and nominations from AIAA, IEEE, and many others. We're excited to hear Julie's thoughts and meet the panelists. She will invite your questions to the panel as well, so please use the QR code on the screen to ask or to upvote a question for the Q&A session at the end. Please join me in welcoming Dr. Julie Shah and our plenary panel to the stage.
Well, good morning and welcome to our plenary panel on AI and autonomy in aerospace. Today we're joined by a very distinguished member, leader in the field. We have Dr. Marco Pavone. He is the lead autonomous vehicle researcher at NVIDIA and associate professor at Stanford University. And Marco leads groundbreaking research in autonomous systems, ranging from self-driving cars to space robotics. He is at the forefront of integrating AI into aerospace applications. And in this conversation this morning, we'll explore the challenges and opportunities in developing trustworthy AI systems for aerospace, discuss the balance between commercial and defense applications, and examine how autonomous systems are reshaping the future of space exploration. So to kick us off, Marco, please share with us a little bit about your current research directions, spanning your work from space robotics to autonomy vehicles.
Well, thank you very much for the introduction. Very happy to be here. Well, let me start by saying that this is a golden age for robotics and autonomy. In the past 2-3 years, there have been a number of breakthroughs in many different disciplines that are really changing the way we architect and we develop autonomous systems. Now, in this context, through my combined roles at Stanford and NVIDIA, I work essentially on 4 main areas. So the first one is about developing foundation models, such as video generation models and vision language models for vehicle autonomy applications. The second one is about architecting, novel ways of architecting autonomy stacks. For example, by leveraging foundation models in different ways as part of the primary algorithmic backbone. The third area relates to simulation technologies to enable end-to-end simulation of autonomy stacks in a realistic and controllable way. And the fourth one is about AI safety. How do we infuse AI methods in safety-critical systems, such as aerospace systems, self-driving cars, and so on. So there are a lot of great advancements. And through my Stanford hat, I primarily apply my work to aerospace systems. Through my NVIDIA hat, I primarily apply my work to self-driving vehicles. And in this context, I would like to highlight a new center that I started with a colleague of mine at Stanford, Simone D'Amico, and with 2 founding partners, Blue Origin and Redward, called the CSER. You have a slide up there. The Center for Aerospace Autonomy Research at Stanford, whose goal is to address unsolved problems in spacecraft autonomy through the judicious incorporation of AI. For example, we are working on ways to use AI techniques, transformer-based models to warm start trajectory optimizers. We are looking at AI techniques for perceptual tasks for aerospace systems. And we're even developing space foundation models, that is, foundation models that take into account the specific inputs and outputs of an aerospace system. So if you're interested in learning more about this center or getting even affiliated with this center, please reach out to me and Professor D'Amico.
Excellent, very exciting. It's just fun and interesting to reflect on how the world has changed in context of AI over the last 1 to 2 decades. When I did my PhD, it was in AI, but in automated planning and scheduling with no machine learning. And when I started my career on the faculty, I remember a colleague at NASA, in talking about the potential for machine learning, told me, don't even think about it. There's no way anything that learns online will ever fly in space. And I sort of filed that away and thought, okay. And then, in the blink of an eye, a few years later, all I did in my lab was machine learning. And so I'm wondering if you can sort of reflect on that timeline. To what extent do you see the importance and potential of systems today that learn and evolve after deployment, and how important is this to the future of the aerospace mission, maybe space exploration in particular?
Sure, that's a great question. So, of course, learning can happen in multiple phases, either at the training time or online through adaptation. For safety-critical systems, I still think that it is hard to conceive a setting whereby the system, adapt its behavior online, also because that might invalidate the validation strategy. For example, in the context of self-driving cars. But for example, for unmanned explorers, to explore, for example, solar system bodies, online adaptation is really needed. And so that's something we are working on. And I see that as a possibility for online adaptation. So I don't think there is like a general answer to this question. It's very much domain specific, but definitely there is a space for online adaptation. I think there is another element though, in the sense that there is adaptation at training time, there is online, but then there is the continual learning aspect of it. So, and this is something, for example, we have been working with the Aerospace Corporation, is once you have deployed an AI system and you have observed, for example, anomalies, how to use those anomalies to retrain your system on the ground so that you can still do validation for your system and then improve it. And I think this is a game changer, for example, in the context of self-driving cars, that you can basically improve your system almost on a weekly basis and update it through over-the-air updates. So, it's a very complicated, I would say, landscape, but with a lot of opportunities.
Very exciting. Thank you, Marco. I'd like to take the opportunity now to welcome our second distinguished leader in the field and panelist, Dr. Eric Smith, Senior Principal in Remote Sensing and Data Analytics at Lockheed Martin Space and the Office of the Chief Engineer. And Eric brings extensive experience in modeling complex systems and applying AI to mission-critical aerospace technologies. Would you please share with us your perspective on how Lockheed Martin is applying AI across the aerospace portfolio in work spanning remote sensing, mission systems, and even generative AI applications?
Yes, so thank you, Julie, and thank all of you for being here this morning. I'm sorry I was a little bit late. So Lockheed Martin comprises a corporate office and 4 business areas: space, missiles and fire control, rotary emission systems, and aeronautics. And we're using AI in every one of those domains. In space, we think about AI for autonomy in unstructured environments like the surface of the moon or Mars. And that would include multi-agent cooperative autonomy for things like manufacturing and assembly. So we, humanity, are going to achieve a permanent human presence on and around the moon. And the moon will be used, among other things, for pushing human exploration deeper into space. And I would foresee the first habitable critical infrastructure on the surface of Mars being constructed by a team of robots and material and tools and high-level instructions that say, do the following things for the humans that are going to arrive here 9 months after they leave the Earth. Looking back at the Earth, autonomy is and will be used for things like land use monitoring and management, coordinated disaster response. It can be used to tip and queue assets and platforms in different domains to track hundreds or thousands or hundreds of thousands of objects on the surface of the Earth, even as they pass under bridges and under cloud cover. Missiles and Fire Control has a department called Advanced Autonomy, and they're concerned with autonomous ground vehicles. And as a way of motivating your thinking on how ground vehicles can really integrate into a bigger picture, I want to think about how an autonomous vehicle in our near future how that might look. So in 2012, there was a Santa Rosa man who was driving north Highway 101 near Sausalito, and he had a heart attack. It's the middle of the night, alone on the highway, had a heart attack. The car left the roadway, sideswiped a steel pole, and crashed near a pedestrian path. And he was found slumped over the wheel by a pedestrian on that path much later that morning. In a world where we have a fully connected autonomous system, that plays out very differently. So you have a man driving alone, Highway 101, has a wearable shirt, watch, ring. The AI on that system detects an impending medical event, finds the nearest ER, plans a route, tells the other autonomous vehicles on the path to clear the path, tells the traffic control system to stop cross traffic along the way, communicates with the ER, lets the emergency room team know what the current situation is, medical history, and when the man arrives, there's a trained team of professionals ready to save his life. We have rotary mission systems, which is a really broad business area. They do a lot of stuff. They're working in everything from helicopters, integrated air and missile defense, littoral, undersea, cyber, EW, C4ISR. And I want to talk about AI in a C4ISR scenario that's relevant today, given what's going on in Southern California with the wildfires, and that's wildfire intelligence. So C4ISR, it's command, control, communication, compute, intelligence, surveillance, and reconnaissance, and that comprises all of the intelligence and information that one needs to understand their environment. What are the threats? What are the assets? It's all of the intelligence and information that's required to formulate a cogent plan of action given the conditions on the ground and the means to carry out those actions. So and that's true in a defense or a firefighting civil case. In the firefighting case, it looks like, let's collect data from space, air, ground, and combine that with environmental data like topography, wind speed, fuel load, humidity, so on and so forth, and allow the AI to generate a future state of that fire line. And the intelligence we provide to the fire chief on the ground is that predicted evolution of the fire line such that he can create a good course of action to save property and lives. Up at corporate, we have an organization called the Lockheed AI Center, the Leigh, and the Leigh has done just a tremendous job of building out all of the infrastructure and tools and processes that we need to develop, train, validate, optimize, and deploy AI to targets of interest to Lockheed. And they've also built a lot of the core components that a lot of the business areas need, some cross-cutting technology. So if space and aeronautics and missiles and fire control all need AI that has as a basic functionality reasoning or decision making, we're not going to build that ourselves. We're going to go to the lake and take the modules that have already been developed for us and integrate those into our programs. That's a short end of what we do.
Excellent. Thank you so much for that tour through the incredible breadth of work that you have in AI. Maybe building on the thread of conversation with Marco, can you comment on in some of those applications, maybe a particular one in which you're thinking about mission critical capability? How do you validate and verify AI systems that are designed to continue learning and evolving after deployment?
Yeah, so today, the way we do this today is exactly the same way we validate the system before we put it out into the field. So we have a means for testing a system, understanding a system in its flight environment, flight space, and for simulating the environment that the system is going to go into. We understand what constitutes nominal operation, and we understand what constitutes stressing corner cases. And there's a strategy before we deliver anything on how we're going to interrogate that the sum total of things that our hardware is going to encounter out in the real world. And when we have a system that's deployed that will learn, I mean, AI systems will learn, they should learn, they're statistical by nature, and they will get better when more information is added to their model. But in the case where these autonomous systems are meant to continue to learning, the system gathers the new data that either adds to its domain or perhaps adds data that was originally out of its domain, and that all goes back to the human operator, and either with an exact copy of the hardware that we have fielded or a high-fidelity digital twin of the hardware that we fielded, we go through exactly the same process of validating its performance in what might now be a new environment, but nevertheless validated by a human and then provided back to the item in the field.
Excellent, thank you. And simulation is certainly a much-needed tool for both development and validation, particularly for aerospace applications. Marco, what do you think are the most recent and important technological breakthroughs that boost our simulation capability? For example, drawing from the field of generative AI.
Yeah, that's a great question. And it's interesting that particularly in robotics, simulation has always been the holy grail in the sense that ideally, if you have a simulator that allows you to develop and validate your autonomy stack, the cost of development will be much lower. In reality, simulation is not used to the extent we would like in a production context because we don't trust the simulator that much. But in the past 2-3 years, again, there have been a number of breakthroughs that have dramatically increased, I would say, both sensor realism and behavioral realism. Like, for example, in the context of sensor realism, there are now techniques falling broadly under the umbrella of neural representations, such as nerves or Gaussian splatting, that have really given us a breakthrough in terms of improving sensor realism, not just for cameras, but also for LiDARs and other sensor modalities. And then combining these reconstruction techniques with generative AI techniques, like, for example, video generation models, now we have technologies to simulate an arbitrary number of scenarios in a very realistic and geometrically accurate way. And even more, we can control the generation process, for example, through language interfaces to generate very targeted scenarios to stress test a system, something that even 2-3 years ago was out of the question. So I think that now we are much closer in using full end-to-end simulation with closed-loop rollouts as part of the development process, and perhaps even for validation purposes.
Very exciting. And in your role in NVIDIA, you have a fair amount of exposure to the automotive sector. Can you talk a little bit about the lessons that you've learned there, and which do you think are most applicable to the aerospace sector?
So, as you all know, like companies such as Tesla, NVIDIA, and many others are investing significantly in fielding AI systems as part of their autopilot systems. So this is to say that by now the automotive community has gathered quite a bit of expertise on the topic of AI safety, both in the context of safety standards that are being developed, but also in terms of guardrails that you need to put in place in order to keep the AI in check. Definitely a validation time, but also at design time, for example, to make sure that the system learns safe behaviors, for example, by injecting rule-based priors, or at deployment time. So basically developing runtime monitors that check that an AI system is operating within its domain of competence. So I think AI safety is a topic where, from the automotive community, that the aerospace community could benefit from. And another one, and this is maybe more futuristic or speculative, is that in the past year or so, the automotive community, again, has been looking at ways of fielding foundation models. Of course, it's challenging, but potentially it's huge. And there again, it could be like there are a number of lessons learned that could be of interest to the aerospace community.
Wonderful, thank you. Sticking on the topic of generative AI, Eric, can you talk with us about how you're using generative AI for dealing with unpredictable space environments, like the Bennu asteroid mission, for example?
Yeah, so that's a great example. So for those of you who may not know, there was a NASA mission called OSIRIS-REx, and the objective of that mission was to rendezvous with the asteroid Bennu and collect a little sample of loose stuff that was going to be on the surface. Lockheed Martin, or one of Lockheed Martin's roles in that was to build the touch-and-go sample acquisition mechanism, or the TAG-SAM. And the idea was the TAG-SAM would show up at Bennu, and we expected a fairly compact surface, and we'd just reach out and grab some of the loose dust and debris that was on top. And Bennu turned out to be more like a ball pit, such that if a human were to stand on the surface of Bennu, they would sink into this loosely gathered collection of dust and rock. And had OSIRIS-REx's reverse thrusters not activated immediately, Bennu 2 would have sunk right into the asteroid. And so we know there are going to be surprises. We can't possibly foresee all of the conditions, the environmental conditions that our probes might encounter when they're in deep space. And one of the approaches that we're taking, we're calling CARL, or causal reinforcement, causal and reinforcement learning. And when we humans encounter anomalies in the world, whether consciously or unconsciously, we try to resolve those through a concept of a causal graph. Given an observation, what are the various conditions that might give rise to that, and what actions can I take to affect a different outcome? And what we're doing with AI is teaching AI to build those causal graphs for environments that we just don't understand right now. Given an environment that we do understand, a human expert can draw that very detailed causal graph, and it is complete. In AI, what we need to start with is, in deep space, start with some things that we know are true, like gravity. I mean, there are things that we can say are universally true no matter where we are. And the AI is then going to have to, through a process of self-experimentation, build the rest of the causal graph to understand how to operate in that new environment.
Exciting. So that speaks to it's a very exciting future of integrating generative AI with simulation that can advance our capability both here on Earth and automotive out to space. In my own work, I think about the integration of AI and human capabilities. And recently I've been thinking about the new challenges posed by generative AI and other deep and highly parameterized models. Just to bring that point into our discussion here, one of my colleagues at MIT, Kate Kellogg, in the Sloan School, conducted a fascinating study recently. So she and her colleagues described this jagged frontier of generative AI's capabilities. It struggles at some tasks, excels at others in ways that can still be very hard to predict. And she explored this with a team of her colleagues at Harvard Business School and Wharton. They conducted a study with over 700 consultants at BCG, giving them two types of tasks. So one was a creative task, leveraging generative AI to support them. And that was a task that was deemed within the capabilities of generative AI to support. And then they gave them an analytical task and to use generative AI in solving essentially an analytical problem-solving problem. And for the creative tasks, the consultants that used the technology saw a 40% boost in their performance. However, for the analytical task, those that chose to use the tool actually performed 19 percentage points worse. They were less likely to arrive at a high-quality solution as compared to those that were solving the problem entirely without generative AI. So they were inappropriately utilizing and relying on this technology, thinking it would support them in this analytical problem-solving task, and it actually undermined their performance. And so, that study highlights the uneven nature of generative AI's potential and the challenges of predicting where it will be most effective, especially the complexity of how that plays with human decision making. Eric, to start with you, in what ways do you see the success and challenges in deploying AI, particularly generative AI, in time-critical missions where human-in-the-loop decision making is necessary?
Well, so the role of AI in decision-making in complex scenarios, I'll say just as a baseline, AI will be trusted to make important decisions in complex environments when it can be trusted to do so. And that, in this study that you just cited, underlines how complicated sometimes the question of how, whether AI can be trusted to do something. There's a long answer to that. But AI will be trusted to make those decisions when it can be trusted to do so. If the environment is so complex or evolving so rapidly that a human can't possibly make an effective decision, we're not going to allow AI to make a bad decision faster than a human can. That's not an option. Now, there are scenarios where decision-making from AI is, I think, going to be totally appropriate and can and is being used today, at least autonomy. And that is in a missile defense scenario where things do evolve very, very rapidly, and the system has been designed for that rapid evolution of events. So we have ground-based radars today called ANTP-2s that, through human-crafted expert rules, know how to detect, track, and discriminate a whole host of objects in a ballistic trajectory that may or may not be threats. and communicate with other ground stations to coordinate a defensive response against these incoming objects. You know, I have seen AI do some pretty amazing things when applied to small signals that are really buried in the noise. So today we live in one of 2 planetary systems that have 8 planets, one of 2. And before 2017, we thought we were the only ones. Even after we had collected a huge amount of data from Kepler, and that data was made publicly available by NASA. Christopher Shalhoub, when he was a Google scholar, applied AI to this massive database from Kepler and found what in December 2017 was confirmed to be the only other 8 planetary system that we know of. And I know that AI can do that same kind of pulling small signals out of the noise in cases where we have objects that may not be all that reflective to the ANTP2 for whatever reason. But the process, AI can be trusted in that decision-making process, decide what we need to worry about that's on a ballistic trajectory and, you know, communicate with the rest of the ground station and hardware to coordinate the response. I also am quite confident that any, you know, offensive attack on the United States would be probably preceded by a cyber attack because, of course, our adversaries understand the architecture of that missile defense system and would like to blind it so that it can't be used. And generative AI can, you know, does play a role in helping, you know, imagine a digital twin of a tactical system that connects all of these assets together, and an adversarial agent that's trying to figure out interesting ways to attack it. And then you of course, have agents that can form effective countermeasures on the defensive side. And having a reinforcement learning trained agent that understands how to reroute and reconfigure a network when it's under attack, I think will be useful in that missile defense system as well.
Thank you. And turning to you, Marco, you know, there's a lot of buzz about LLMs, and you've mentioned them a bit in your remarks about the potential of leveraging generative AI with simulation, and in your opening remarks as well. Can you elaborate on your view of the potential benefits of this technology for the purposes of aerospace?
Sure. I mean, LLMs are part of the broader family of foundation models. And here I want to be specific about what I mean by a foundation model, since sometimes this term is used a little bit in a confusing way in the community. Here, by foundation model, I mean a model that has been trained on broad data, typically at the internet scale and in a self-supervised manner. And it can be adapted or fine-tuned to a wide range of downstream tasks. And examples of foundation models include large language models, vision language models, video generation models. It's, you know, a full family. Now, typically, foundation models, such as vision language models, are discussed in the context of improving the primary algorithmic backbone, so basically the onboard autonomy stack. And there is definitely a lot of value there, and this is something that we are doing also in my labs, both at Stanford and NVIDIA. But I think foundation models have the potential to really empower the full development process of an autonomous systems, from data curation, for example, by providing you know, extremely powerful auto-labeling tools or search tools to search the data that you really need in order to fine-tune a given model, to simulation, as we discussed, to evaluation, so basically to automatically evaluate, for example, the performance of a system in order to kick off a data flywheel, to safety, for example, acting as a runtime monitor, as it was discussed before, and of course to the onboard stack. So the point here is that there are a lot of possibilities actually at NVIDIA, and now we're heavily using foundation models as part of the offline development processes in addition to the onboard stack. Surely some of these applications will not pan out as we expect, but there are so many application opportunities that it stands to reason some of them will be game changers.
Excellent. And this is a wonderful time for us to turn to our audience questions. As a reminder, please use the QR code on the slide to submit or to upvote a question. And so building on this discussion, for both of you, a question, given the tendency for LLMs to hallucinate, how can trust be built for critical systems which are using AI?
How can trust be built with LLMs? So, I mean, the obvious current way people are doing it is by using RAGs. So we're gonna instead of just having the LLM rely on the vast library of things that it's run across in the world, we're going to point it to a trusted database of known documents. As Lockheed Martin is using this for one of its internal business purposes. As an example, it's a really bad idea in certain temperature regimes to hard mount an aluminum ring around an optic, but people tend to do it all the time. It's probably in 500,000 pages of white papers and engineering memos and lessons learned that's in a variety of Lockheed Martin databases, and we're using AI to generate responses by pointing it directly to that trusted set of documents.
And I mean, so as I'm just to say, LLMs are not black magic, right? So they are data-driven models, albeit very large ones, but they're essentially data-driven models. And as with all data-driven models, there is a potential for this model to operate out of distribution and give erratic responses. And this is something that the machine learning community and the autonomy community has been dealing with actually for decades now. Of course, this is exacerbated in the context of LLMs, but I wouldn't say is a new problem. And there is no single answer. Of course, robustifying LLMs, there are a number, or foundation models in general, there are a number of techniques. But in general, building guardrails, so essentially specifying domains, perhaps even with physics intuition with respect to which an LLM is allowed to plan. Like, for example, in trajectories, providing essentially a space within which an LLM is allowed to plan. And if that space is violated, then rely on a classical stack for safety, whether they are using LLMs more for improving performance. So it's about guardrailing, robustifying them, but also acknowledging that is, inherent problem with all AI system is not a new problem, and we have a number of tools at our disposal.
Excellent. Thank you both. Thinking about the fast-moving pace of this technology and the role of the sort of commercial enterprise in maturing this technology, how do each of you think about the criteria to determine which AI applications should be developed in-house versus leveraging existing commercial solutions? Equally relevant in industry as in research labs today.
Yeah, so there are these kind of obvious supply chain things that one has to think about, export control restrictions or risk associated with a single supplier for a critical technology. But in general, at Lockheed, if there is a commercial solution that works, that's been verified and is trusted and can be transferred into the use case of interest, and there are several checkboxes there that say can or cannot be transferred, and that kind of gets complicated. But the point is, if it can be used and there isn't risk and cost and regulatory associated with it, we want to use a commercial solution. And not only do we want to use and leverage what's going on in the commercial world, I mean, it's just a mind-blowing amount of work, and anybody would be crazy not to want to be able to leverage all of that. So not only do we want to use it, we want to foster the growth in these disruptive companies that are operating in markets that are aligned with interests of Lockheed Martin. So we have an organization called Lockheed Martin Ventures. It was founded in 2007, and we have invested over $200 million in 35 companies worldwide for that very purpose. Let's find these companies that are aligned with markets that we're interested in and help them grow.
I mean, I think this is a super difficult question that I'm sure that you also grapple with, right? It depends on so many different things. Of course, know-how that you have in your lab, cost of the commercial solution, time, pressure, opportunities for strategic partnerships, and so on and so forth. So it's very tricky. I don't think there is a general answer to that. In academia, we are somewhat fortunate in the sense that in many cases, commercial solutions are provided through academic licenses free of use. So somehow on the academic side, the decision is easier because we can access high-grade commercial solutions almost for free. But yes, that's a very tricky question.
Excellent. And what would you say are the key challenges in scaling AI-driven autonomy from experimental systems to operational aerospace environments, especially given safety-critical constraints?
So there are a lot of challenges. Let's see. I'll point to one in particular. I mean, the military is 500,000 highly trained, very specialized people who have a set of tools and procedures that they follow to do their jobs. There are accepted, quote unquote, tradecraft that people at, say, NGA will use when they're operating on all of this geospatial data to help warfighters make decisions. And in order for, it's more than just learning to a lot of the discussion around AI today is about trusting the AI. And I think we can build, and you might have to handcuff the AI pretty significantly, but you can build AI and autonomy solutions that can be verified and trusted, and we can ensure that they are operating only in their domains. We're not going to be operating on out-of-domain data, or we have ways of flagging data that looks like it's out of domain. I think a big challenge is in getting the people who are developing the AI at that experimental level to understand the intricacies and details of how the end user actually wants to use this. Build it in a way that is going to make somebody's job more effective and easier and not harder and more complicated and just add cycles to their day, because it'll never get used. So I think anything that we can do to bring people who are using the technology in the field and the people who are developing it in the lab closer together for extended periods of time is the best thing to do. And I ask people all the time at Lockheed who are developing these kinds of fundamental solutions whether they understand who it's going to help and how it's going to help them. And if they don't, we get them together so they can talk.
I think that's a great question. I mean, I think the key challenge is that you need to transform your organization into a data factory organization. And that's easy to say, but extremely hard to do. So how you transform your organization into an organization that you can ingest enormous amount of data, probably channel all the data through different workflows with very high quality for heterogeneous data, particularly in the context of autonomy for different tasks, with the goal of essentially delivering uniformly available high quality levels throughout an organization of thousands of people. Mm-hmm. It's extremely challenging because it changes completely your workflows. It also requires different talent, a change in mindset. So organizationally is a tremendous challenge. But that's what you have to do. If you have a bespoke solutions in the ways that you deal with your data, there is no way you're going to scale. Mm-hmm. Organizationally, your organization is going to be fragmented, and at the end, you're not going to really deliver at the specs that you need for a product.
Absolutely. And another factor is most certainly, the path towards certification. So one of our most upvoted questions here is, what do you see as the path towards certification of non-deterministic software?
So again, the way we today, and this is a big challenge, this is a challenge on how to handle this in the future, but today we certify and validate artificial intelligence and autonomy-based systems in the same way that we certify and validate any system pre-delivery, and that is, it doesn't operate on new data in new domains without having model updates overseen by humans. And I think that is that remains a challenge. What is the process? And it has to be solved at some point. You know, we talked about this Bennu example. I mean, one of my favorite planets in the solar system, Earth first, you know, Earth is pretty good. But my next favorite place in the solar system is Europa. I'm just fascinated by it. And we're going to go to Europa at some point. And when we land on Europa, we're going to find things we didn't know about. We're going to have to generate these new causal graphs. The system is going to have to learn how to operate in a pretty different environment. But we don't want to stay on the surface. We want to go down under the surface. And as we're tunneling through that kilometer of ice sheet, things are going to get even weirder. And we can't have the probe stop and talk to Earth, which is a 45-minute one-way trip for a photon, for a message to get back, and then back and back and forth. That's just not going to work. And when we get through the ice sheet into what we think is a liquid ocean, it's going to get even weirder. And so that system, we have to have a way of trusting that an evolving, learning system is going to do so without causing itself or its surroundings harm. But today, the way we do those updates and the way we treat generative models or models that are supposed to change after they're deployed is any changes to the model has to be overseen by a human.
I mean, I'll admit that I'm more familiar with the certification problem in the automotive context rather than the aerospace context. But that said, I mean, for some components, we do have quantitative techniques to certify the system. For example, for neural networks with a well-defined input space, well-defined output space. This is typically the case of controlled neural networks. We do have a neural network verification tool that can quantitatively give you an answer about whether the system is safe or unsafe. But when you put everything together so you have a full autonomy stack, I think that the solution has to be, to a large extent, empirical. Of course, in the design process, you take care of building a redundant pipeline and so on and so forth. But then to really prove that it is safe, most likely you need to rely on an empirical process. For example, in the automotive context, you set up targets in terms of a mean time between failures, and then you try to demonstrate that you can achieve those targets based on data that is gathered through a test, to a test fleet. Of course, it would be wonderful if we could use a simulation to help us with the validation process. But of course, that introduces the topic of validating the simulator itself in the sense of whether you trust the KPIs. And actually, this is a topic that we are working on. And I see a future where the validation process, not for the first time that the system is fielded, but for the subsequent times, this process can be actually aided through simulation tools.
That's a great way to tie many of our discussion points together with a forward-looking vision. We can wind up here with our last top upvoted question here, which I believe is for Eric. Is any of the mentioned firefighting intelligence capability being tested and deployed in California right now?
It's not being deployed in California. To my knowledge, it is being tested in California and Colorado. We're working with fire agencies in both states. You know, in the California situation is a little bit different, speaking about the generative AI and how do you validate a system that's working, potentially out of domain. I think the firefighting, certainly a fire line evolution in nominal conditions in the Sierra Nevada or the Rocky Mountains is going to look significantly different from 100-mile-an-hour Santa Ana wind-driven fires in a mixed suburban wildland area. And so that, what's going on in Southern California right now is going to add a whole bunch of out-of-domain data for these agents to improve in the future. But short answer to the question is, to my knowledge, we're not deploying or using that in California at this time.
Thank you. Thank you, Eric and Marco, for this fascinating discussion. And thank you to our audience today.